Hello. So this center of mass, we already discussed the center of mass. We need to discuss conservation of linear momentum, conservation of I mean angular momentum. So for that, we use many particle system. This is our center of mass equation. So this one, mr equal to summation I equal to 1 to n mi r, right? So these are all things we already discussed in previous class. So now we are going to discuss conservation of linear momentum. So as we know, mr equal to m is the total mass of the system. Okay, r equal to summation I equal to 1 to n mi ri. Now I'm going to differentiate with respect to time t. Then m dr divided by dt equal to m1 dr divided by dt m2 and so on nth particle. So after that, this is what I got. Okay, rate of change of position is nothing but velocity up to n particle system. So this I am going to use summation I equal to 1 to n mi vi. Here I is I equal to 1, 2, 3, 4, and so on up to n. So which gives the velocity of the center of mass. The sum mv, mass into velocity, is equal to p, is the total linear momentum of all the particles of the system, not the individual particle of the system, all the particles of the system. We are talking about many particle system, not in single particle system. Those p equal to m. The total linear momentum of the system is equal to the product of the total mass of the system and velocity of the center of mass. So now I am going to differentiate p equal to mv. Let us see what will happen. So dp divided by dt, linear momentum mv, and m is constant with respect to t derivative. So then velocity we can write d square r divided by dt square. Okay, position, right? Two derivative of position. Now if you observe carefully here, this one is a external force of the system. Okay, nothing but rate of change of momentum is nothing but force. We know Newton's second law. This force is external force. So from that information, what we understand, uh, external force rate of change of momentum is nothing but mv, where this external force equal to 0, then momentum is equal to constant. Thus, if the total external force on a system is 0, its total linear momentum is the constant of motion. This is the law of conservation of linear momentum for a system. We already discussed conservation law starting of this series. So the difference between these two conservation laws, that is just we discuss about one particle system conservation law. This is actually classical mechanics system conservation law, many particle system conservation law. So it is better to focus on this type of conservation law. Okay. Next, conservation of angular momentum. If J1 and J2 and so on Jn are the angular momentum of the various particles of the system, then the total angular momentum is given J equal to J1 plus J2 and so on up to Jn. So Rj equal to R cross P, right? Then we can extend this one R cross P up to r cross p into n. Okay, then you can sum up this one, we'll get this one. Here I equal to 1 to n particle system. Okay, which means n particle system we are talking about. N particle. Okay, not in n particle system and n particle system angular momentum. So this is n particle system angular momentum. So now I'm going to try to derive with respect to t this equation. If you try to apply dt here, then apply here uv form. First this one constant, derivative here I'm using dot means d by dt, plus p constant r derivative r dot d by dt, here I'm using r dot means derivative. Okay, so if you look carefully here, the p dot is nothing but force. Okay, I mean rate of change of moment is nothing but force. Here r dot is nothing but velocity into momentum of the system, I particle system momentum MIVI. So if you try to cross product this thing, it will go into 0. Okay, we have this. So this is what we got. So here Fi is the total force of the system. We already know external force, total force is split into two type of force. One is external force, another one is internal forces. So here Fi is, I'm going to split this thing. So we know already many particle system. We talk about this thing. Fi E means external force plus summation of all the particle interactions. So if you try to extend this one, you'll get this type of thing. Simple, right? R cross Fe plus R cross summation F suffix I J. Here, if you observe carefully here, so this one R cross Fi, what is meaning of this one? So this one I'm going to use 0 because since Fi equal to minus Fji, it's going to 0 if you apply the cross product. Then dj divided by dt equal to this r cross f is nothing but torque tau, external torque, external torque. So divided by dt equal to tau. E means external torque of the system. This means the time rate of change of total angular momentum of a system of particles is equal to the applied external torque on the system. If torque is equal to 0, then dj divided by dt is equal to 0, and j is equal to constant. And what factor this conservation law is going to tell the physical quantity is constant in time. Okay, and under the what conditions? Okay, the limitations are there. Under what condition this angular momentum j is equal to constant. So therefore, total angular momentum of n particle system, we are going to into j1, j2, j3, and so on, j and sum of, we're simply using total j, total angular momentum of the system, it is equal to constant. In the absence of external torque, the total angular momentum of a system of a particle is conserved. This is the conservation theorem for the total angular momentum of many particle system. So right now we discuss conservation laws, two conservation laws, and few fundamental topics. Next class I am going to address about what are the limitations of these conservation laws. Is conservation laws are valid any system or not? For example, if we try to I'm going to try to apply these conservation laws on Boyd-Schacht law. If it is for total angular momentum of system, I mean conservation of angular momentum, conservation of linear momentum. So if you want to know these questions answered, you need to wait next class. Next class I am going to address about this validity of conservation of linear momentum, validity of conservation of angular momentum.